the farthest edge of what humans can observe, something has been found that should not exist. Not a small error, not a minor anomaly, something that quietly breaks the expectations of modern physics. For decades, scientists believed they had a stable picture of the universe, a structure governed by predictable laws, a cosmic timeline that begins with the Big Bang and expands in a smooth, measurable way. But now, deep space observations are showing something different, something unsettling. Either our understanding of the universe is incomplete, or reality itself is behaving in ways we never expected. This is not speculation without evidence. This comes from real data, collected by some of the most advanced telescopes ever built. Instruments designed to look farther into space than any human technology before them. And what they are revealing is forcing scientists to ask a difficult question. Is the universe still following the rules we think it does? To understand why this matters, there is something important to clarify first. When scientists talk about the edge of the universe, they are not referring to a physical boundary. There is no wall out there. There is no point where space suddenly ends. Instead, there is something called the observable universe. This is the limit of what we can see. It is defined by how far light has had time to travel since the beginning of everything. Because light has a speed limit, and because the universe has been expanding for billions of years, there is a horizon beyond which we cannot receive any information. No matter how powerful our telescopes become, we are always looking back in time, never directly into the present state of those distant regions. So when scientists point their instruments toward the deepest parts of space, they are not just looking far away. They are looking back billions of years into the early universe itself. And this is where things begin to become strange. Modern telescopes are now reaching deeper into this cosmic history than ever before. They are capturing light that started its journey almost at the beginning of time. They are mapping galaxies that formed when the universe was still young and chaotic. For a long time, the expectation was simple. The further we look, the more uniform and predictable the universe should appear. Early cosmic structures should follow clear patterns. Expansion should behave in a consistent way. The laws of physics should remain stable across all distances. But recent observations are not fully agreeing with that expectation. Instead of a smooth and consistent universe, scientists are finding subtle inconsistencies, patterns that should not be there, structures forming too early, expansion rates that do not align, temperature variations in ancient light that appear slightly off balance. At first, each of these findings was treated as a separate issue, a possible measurement error, a limitation of technology, a statistical coincidence. But as more data has arrived, a troubling pattern is beginning to emerge. These anomalies are not isolated. They are appearing in different parts of the sky, from different telescopes, using different methods of measurement, and yet they seem to be pointing in the same direction. Something fundamental may not be fully understood. To many outside the field, this might sound like a small scientific adjustment, a minor correction to existing models, but in cosmology, even the smallest inconsistency at the largest scales can signal something much deeper. Because the universe is not just a collection of stars and galaxies. It is a system governed by a small number of physical laws. If those laws fail to explain what is being observed at the edge of everything we can see, then the problem is not local. It is foundational. And this is where the tension begins to build. Scientists are now facing data that refuses to fully fit into existing theories. Data that suggests the early universe may have evolved differently than expected. Data that raises questions about whether the expansion of space is behaving exactly as predicted. Data that hints at irregularities in the oldest light that still reaches us today. None of these findings alone is enough to overturn modern physics. But together, they are becoming increasingly difficult to ignore. Because the deeper we look into the universe, the more it seems to resist a simple explanation. And that leads to a question that sits at the center of this entire mystery. If everything we know about physics is correct, then why is the farthest observable universe showing signs of inconsistency? To answer that, we need to go step by step through what scientists are actually seeing, starting with the most fundamental concept of all, the true nature of the cosmic boundary itself. The idea of an edge of the universe sounds simple at first, a final boundary, a place where everything ends. But in modern cosmology, no such wall has ever been found. There is no confirmed physical edge to the universe, no border where space stops, no cosmic limit where reality breaks. Instead, there is something far more strange. There is only an observational boundary. This boundary is not made of matter. It is not a structure. It is defined by time and light. Everything we can see in the universe is limited by one simple fact. Light travels at a finite speed. It moves fast, but not instantly. Because of this, we are always looking into the past when we observe distant space. The most distant light we can detect has been traveling for billions of years. It started its journey when the universe was extremely young. That means every galaxy, every star, every faint glow at the farthest edge of our telescopes is not seen as it is now, but as it was long ago. This is the observable universe, a sphere of space defined by how far light has reached us since the beginning of everything. But there is another layer that makes this even more complex. The universe is not just expanding, it is expanding faster over time. Space itself is stretching. This means that some regions are moving away from us so quickly that their light will never reach us at all. So the observable boundary is not just about distance. It is also about expansion. Some parts of the universe are permanently hidden from view, not because they are too far, but because space is pulling them away faster than light can travel toward us. This creates a strange situation. We are not seeing the universe as it is today. We are seeing a layered timeline of its past. Different distances show different ages. Closer galaxies appear more recent. Farther ones appear younger. At the very edge, we are looking almost directly into the birth of cosmic structure. This is why this boundary is so critical. It is the only window we have into the early universe. Every theory about how galaxies formed, how matter spread, how space expanded, all of it depends on what we observe at this limit. And this is where things begin to become unstable. At these extreme distances, even the smallest irregularity becomes important. A slight difference in galaxy formation speed, a tiny shift in background radiation, a subtle mismatch in how fast expansion is measured. These are not just small details. They are clues that test the entire framework of cosmology. Because when scientists build models of the universe, they rely on consistency across all scales. If the early universe behaves even slightly differently than expected, then every later structure must be reconsidered. That is why the observable boundary is not just a distant horizon. It is a testing ground for reality itself. And recently, that testing ground has started to show results that do not fully match the predictions. Tiny inconsistencies are appearing in the oldest light. Unexpected patterns are forming in the distribution of galaxies. Measurements of distance and expansion are not aligning perfectly. Each one alone might be dismissed, but together they suggest something deeper is happening at the farthest reaches of what can be seen. Something that forces scientists to question whether the rules applied everywhere in space are truly universal. Long before galaxies formed, long before stars lit up the sky, the universe was filled with a faint glow that still exists today. This is the cosmic microwave background, often called the CMB. It is the oldest light in the universe. It was released when the universe was only about 380,000 years old. At that time, space was still hot, dense, and filled with a glowing plasma. Light could not travel freely. It was constantly scattered. Then something changed. The universe cooled enough for atoms to form. Electrons combined with nuclei. For the first time, light could move through space without constant interference. That moment left behind a signal, a faint microwave glow stretching across the entire universe. Today, that glow is still everywhere. It fills all directions. It is almost perfectly uniform. Every region of the sky shows nearly the same temperature. The differences are extremely small, measured in fractions of a degree. For decades, this uniformity supported a major idea in cosmology. The early universe was smooth, simple, predictable. Any tiny fluctuations were thought to be random seeds that later grew into galaxies. But modern measurements have revealed something unsettling. The cosmic microwave background is not perfectly uniform. There are strange cold spots, regions slightly cooler than surrounding areas. Some of these areas are far larger than expected. They stretch across vast portions of the sky. One of the most debated examples is a massive cold region that appears too large to be easily explained by standard models. Its size alone raises questions about how such a structure could form in a universe that was supposed to be nearly uniform at that stage. Even more unusual is the pattern of asymmetry across the sky. One, half of the universe, as seen in the CMB, appears slightly different from the other. Not dramatically different, but enough to be statistically noticeable. This breaks a key assumption, that the universe on the largest scales should look the same in every direction. Scientists refer to this as large-scale isotropy, and the CMB data is showing possible cracks in it. At first, many researchers thought these anomalies were just statistical noise, random fluctuations that naturally appear when dealing with such enormous data sets. After all, when you measure something across the entire sky, small irregularities are expected. But the more data collected, the more persistent these patterns became. Different satellites confirmed similar results. Independent analysis methods pointed toward the same irregular features. The cold spots and asymmetries did not disappear with better measurements. They remained. This led to a growing debate in the scientific community. Some argue that the anomalies are still within the limits of chance, that the universe is large enough for rare statistical events to appear naturally. According to this view, nothing fundamental is being challenged. Others see a different possibility. They suggest that these patterns might not be random at all. They could be hints of unknown cosmic structures, effects from regions beyond the observable universe, or even signs that early cosmic conditions were influenced by physics we do not yet understand. There is also a more subtle concern. If these irregularities are real and not statistical noise, then they might be connected to deeper issues in cosmology. Because the cosmic microwave background is not just ancient light. It is a direct snapshot of the universe at its earliest readable moment. Any distortion in that snapshot carries forward into every model built on top of it. And that means even a small irregular pattern in this ancient glow could ripple through our entire understanding of how the universe began and how it evolved. As telescopes push deeper into space, scientists expected to find simple, small, and immature galaxies in the early universe. That is not what they saw. Instead, they began detecting galaxies that should not exist at that point in cosmic history. These galaxies appear far too massive, far too organized, far too evolved for their age. According to standard models, galaxies take time to grow. They begin as small clouds of gas. Gravity slowly pulls matter together. Stars form over long periods. Mergers and collisions build larger structures. This process should take hundreds of millions of years. But observations from deep space suggest something very different. Some galaxies appear fully formed only a few 100 million years after the Big Bang. Not small clusters, not weak early structures, but large, bright, and mature systems that look surprisingly developed. This creates a direct tension with current theories. The timeline of galaxy formation may be much faster than expected. In some cases, the brightness of these early galaxies suggests they contain billions of stars. That level of mass so early in the universe should be extremely difficult to achieve under known physics. Even more surprising, some of these galaxies show signs of chemical maturity. Elements heavier than hydrogen and helium appear in higher amounts than expected. These heavier elements are produced inside stars, meaning multiple generations of stars must have already lived and died. That process takes time, yet these galaxies appear to have completed it far earlier than predicted. This has forced scientists to reconsider one basic assumption: that structure formation in the early universe was slow and gradual. Instead, data is pointing toward a much more rapid evolution. One lesser-known detail is how difficult these observations are to confirm. Early galaxies are extremely faint and red-shifted. Their light has stretched across billions of years of expanding space. This makes them hard to detect and even harder to analyze accurately. Because of this, early discoveries were met with caution. Some researchers suggested measurement errors. Others questioned whether the galaxies were truly as distant as they appeared. But as new telescopes improved, the evidence became stronger. Independent observations began to confirm the same pattern. Multiple instruments detected galaxies at extreme distances with surprisingly advanced structures. This reduced the likelihood of simple observational mistakes. Now, a deeper question is emerging. If these galaxies are real and their properties are correctly measured, then something about the early universe must be different from what current models assume. One possibility is that matter clumped together more efficiently than expected. Another is that unknown physical processes accelerated star formation. There are even ideas suggesting that the conditions of the early universe allowed faster cooling and faster collapse of gas clouds. Each explanation introduces new complexity, because none of them are fully supported by established physics. And this leads to a more unsettling implication. The early universe may not have followed the same rules we observe today. It may have evolved under conditions that are still not fully understood. If that is true, then the story of galaxy formation is not just incomplete. It may be built on assumptions that only apply to a later stage of cosmic history. For a long time, scientists believed they had a reliable way to measure how fast the universe is expanding. This number is known as the Hubble constant. It tells us how quickly galaxies are moving away from each other as space itself stretches. It is one of the most important values in cosmology. It connects the past, present, and future of the universe. But there is a problem. Two completely different methods of measuring this expansion do not agree. The first method looks at the early universe. It uses the cosmic microwave background, the ancient light left over from the Big Bang. By studying tiny fluctuations in this light, scientists can calculate how fast the universe should be expanding today based on standard physics. The second method looks at the local universe. It measures distances to nearby galaxies using special stars and supernovae that act as cosmic markers. These measurements track expansion more directly in the modern universe. Both methods are highly advanced. Both are carefully tested. Both are based on strong scientific principles. And yet they give different answers. Not slightly different, significantly different. The early universe method suggests a slower expansion rate. The local universe method suggests a faster one. The gap between them is too large to be explained by normal measurement errors. At first, many scientists thought this would disappear with better data. Small mistakes often happen in complex measurements. Instruments improve. Calibration gets refined. Values usually converge over time, but that is not what has happened. As measurements have become more precise, the disagreement has become stronger. This growing conflict is now known as the Hubble tension. It has become one of the biggest open problems in cosmology. What makes it more unsettling is that both results come from entirely different parts of the universe and completely different physical methods. One relies on the ancient past. The other relies on the relatively nearby universe. Yet both should lead to the same final value if our understanding of physics is complete. That consistency is missing. This has led to serious questions. If there is no error in the measurements, then something in the underlying model of the universe may be incomplete. One possibility is that the early universe evolved under slightly different physical conditions than expected. Another is that unknown forms of energy could be affecting expansion in subtle ways. Some researchers have even proposed new particles that interact weakly with known matter. Others suggest additional forces that only become significant at cosmic scales. There are also ideas that gravity itself may behave differently over vast distances than it does locally. None of these ideas are confirmed, but they are being studied seriously because the data refuses to align. There is also a lesser-known detail that adds more pressure to the problem. Multiple independent research teams using different telescopes and different data sets have all reached similar conclusions. This reduces the chance that the discrepancy is caused by a single systematic error. Instead, the disagreement appears to be built into the observations themselves, and that raises a deeper concern. If the expansion rate of the universe cannot be consistently measured using two fundamental approaches, then something about the structure of cosmology may need revision, because expansion is not a small detail. It is the backbone of how the universe is understood across time. There is a force in the universe that no one has ever directly seen, yet it shapes everything on the largest scale. It is called dark energy. It is responsible for one of the most surprising discoveries in modern science. The universe is not just expanding, it is accelerating as it expands. Galaxies are moving away from each other faster and faster over time. This was first discovered through observations of distant supernovae. These exploding stars acted like cosmic markers. They showed that the expansion of the universe is not slowing down under gravity as once expected. Instead, something is pushing space itself apart. That something was named dark energy, but the name hides a deeper truth. Scientists do not know what it actually is. It does not emit light. It does not reflect light. It does not interact with matter in any known way. It is only detected through its effect on the expansion of the universe. In the simplest model, dark energy is treated as a constant, a fixed property of space itself, something that has always existed and always has the same strength everywhere. This idea fits many observations, but not all. Recent measurements have begun to hint at a more complicated picture. Some data sets suggest that dark energy may not be perfectly constant over time. Instead, it may be slowly changing. This is a subtle shift, but its consequences are enormous. If dark energy changes even slightly, it would affect how the universe expands at every stage of its history. It would alter the timeline of galaxy formation. It would change predictions about the future structure of the cosmos. And most importantly, it would break one of the key assumptions in modern cosmology, that the laws governing the universe are fixed and unchanging across time. There is also a lesser-known detail that adds to the mystery. When scientists combine different types of observations, including supernova data, galaxy surveys, and cosmic background measurements, they sometimes find small inconsistencies in how dark energy behaves in each data set. None of these inconsistencies are large enough on their own to prove a change, but together they form a pattern that is difficult to ignore. This has led some researchers to explore more radical ideas. One possibility is that dark energy is not a single entity. It could be a dynamic field that evolves over time. Another idea suggests it may interact weakly with other unknown components of the universe, causing subtle shifts in expansion. There are even proposals that gravity itself may not behave exactly as described at the largest scales, and that what is being labeled as dark energy is actually a sign of deeper changes in gravitational behavior. None of these ideas are confirmed, but they are being seriously investigated because the standard model leaves too many questions unanswered. The most unsettling part is that dark energy makes up most of the universe, roughly. 70% of everything that exists is tied to this unknown force, and yet its nature remains completely hidden. If it is truly changing over time, then the universe is not following a simple fixed rule set. It is evolving under conditions that are still being uncovered, one observation at a time. Across the deepest parts of the universe, a strange pattern begins to appear. At first, each discovery seems separate. A cold spot in ancient radiation, galaxies forming too early, two different answers for how fast the universe is expanding, a mysterious force driving acceleration that nobody fully understands. Individually, each result could be explained away, a measurement issue, a statistical fluke, a missing detail in a complex model. But when all of them are placed together, the picture becomes harder to ignore. The cosmic microwave background shows subtle irregularities in the oldest light we can observe. Early galaxies appear far more advanced than they should be. Expansion rates refuse to agree between early and modern measurements. Dark energy, the dominant force in the universe, may not even be constant. None of these points fully breaks modern physics on its own. But together, they form a quiet tension across the entire structure of cosmology. A structure that once felt complete now feels unfinished. The universe still behaves with incredible precision at smaller scales. Gravity works. Light behaves predictably. At human and even galactic levels, the rules remain strong. But at the largest scales, where space itself stretches across billions of light years, something does not fully align. It raises a difficult possibility. The problem may not be that the universe is breaking the rules. The problem may be that the rules we are using are not the final version. Physics has always advanced by confronting contradictions. Small mismatches in data have often led to major breakthroughs. New particles, new forces, entire new frameworks of understanding. This moment feels similar, but on a far larger scale, because now the inconsistencies are not local. They are cosmic. They appear in the oldest light, the farthest galaxies, and the expansion of space itself. If even one of these tensions turns out to be real and fundamental, it could reshape how the universe is understood from the ground up. And that leads to a quiet but powerful thought. The universe may not be wrong. It may simply be more complex than the current picture allows. A final layer of reality may still be waiting to be uncovered, hidden in the deepest parts of space, just beyond what has already been measured. If you enjoyed this journey into the edges of what is known, take a moment to like the video and subscribe to the channel. There is still much more to explore, and the universe is far from finished revealing its secrets.